This lecture is on Lewis dot structure, specifically on covalent compounds. Here in this figure, there are two words we need to know, duet and octet. Duet means an atom surrounded by two electrons. You can see that with hydrogen. Octet means an atom surrounded by 8 electrons. You can see that with oxygen. Note before we move on, the electrons may be shared or unshared. Next, we will discuss how electrons are arranged for a species. Here is a figure of water with a molecular form of H2O. It shows the 2 bonding pairs and 2 lone pairs on the O atom in water's Lewis dot structure. Electrons that are shared by atoms are called bonding pairs. Electrons that are not shared by atoms but belong to a particular atom are called lone pairs, also known as non-bonding pairs. Below is an illustration of SO2 where there are 2 bonding pairs and 1 lone pair around the S atom. Lewis atomic structures can be used to predict the expected bonding between non-metal atoms. Non-metal atoms often bond to achieve an octet of valence electrons by sharing electrons, though there are many exemptions to the octet rule. In Lewis theory, atoms share electrons to complete their octet. This may involve sharing electrons with multiple atoms or sharing multiple pairs of electrons with the same atom. Single covalent bonds have 2 electrons shared between atoms. 2 examples illustrating this are F2 and H2O. A line represents 2 electrons shared between atoms. Double covalent bonds have 4 electrons shared between atoms. An example illustrating this is O2. An equal sign represents 4 electrons shared between atoms. Triple covalent bonds have 6 electrons shared between atoms. An example illustrating this is N2. An equivalence or a triple line represents 6 electrons shared between atoms. The more electrons 2 atoms share, the stronger they are bonded together. This explains the observation that triple bonds are stronger than similar double bonds, which are stronger than single bonds. This explains the observation that triple bonds are shorter than similar double bonds, which are shorter than single bonds. Here below is a table showing the relationships between bond type in correspondence to A length and B energy. More electrons shared between atoms, the shorter the bond length and the higher the bond energy. Polyatomic ions are attracted to opposite ions by ionic bonds. Atoms in the polyatomic ion are held together by covalent bonds. An example shown is Cn-. For Lewis forms of molecules, some common bonding patterns are needed to be known. C, or carbon, has 4 bonds and no lone pairs. 4 bonds could be any of the following. 4 single bonds, 2 double bonds, a single and triple bond, or 2 single and a double bond. N has 3 bonds and 1 lone pair. O has 2 bonds and 2 lone pairs. H and halogens have 1 bond. Be has 2 bonds and no lone pairs. Boron has 3 bonds and no lone pairs. Writing Lewis structures for covalent molecules are as follows. 1. Attach the atoms together in a skeletal structure. Most metallic element is generally central. Halogens and hydrogen are generally terminal. Many molecules tend to be symmetrical. In oxyacids, the acid hydrogens are attached to an oxygen. Calculate the total number of valence electrons available for bonding. Attach atoms with pairs of electrons and subtract electrons used from total. Add remaining electrons in pairs to complete the octets of all atoms. If there are not enough electrons to complete the octet of the center atom, bring pairs of electrons from an attached atom to share with the central atom until it has an octet. An example is HNO3. Write the skeletal structure where N and O are the center atoms. Count the valence electrons, which is 24 electrons. Attach atoms with pairs of electrons and subtract from the total. There are 8 electrons used and 16 electrons left. Complete octets from outside or terminons until an octet arrangement is attained. If center atom does not have an octet, bring in electron pairs from outside atoms to share. Here in this practice exercise, some additional problems for you to try. The question is, draw the Lewis structures of the following molecules. We have H2S, NH3, and PCl3. Rules for writing Lewis structures for polyatomic ions. The procedure is the same, the only difference is in counting the valence electrons. For polyatomic cations, take away 1 electron from the total for each positive charge. For polyatomic anions, add 1 electron to the total for each negative charge. An example is NO3-. Write the skeletal structure where N is the central atom. Count the valence electrons, which is 24 electrons. Attach atoms with pairs of electrons and subtract from the total. There are 6 electrons used and 18 electrons left. complete octet on outside or terminals until an octet arrangement is attained. If the central atom does not have an octet, bring in electron pairs from outside atoms to share. For ions, bracket the structure with charge stated. Here are some practice problems for you to work on. Draw the Lewis dot structure per species. NClO, H3BO3, NO2 minus 1, H3PO4, SO3 minus 2, and P2H4. Exemption to the octet rule. H and Li lose one electron to form a cation. Be shares 2 electrons to form 2 single bonds. B shares 3 electrons to form 3 single bonds. Expanded octets for elements in period 3 or below. And the reason? They have empty valence d orbitals. Some molecules have odd number of electrons. We call them radicals. An example is NO. Resonance means the following. We can often draw more than one valid Lewis structure for a molecule or ion. In other words, no one Lewis structure can adequately describe the actual structure of the molecule. The actual molecule will have some characteristics of all the valid Lewis structures we can draw. Lewis structures often don't accurately represent the electron distribution in a molecule. Real molecule is a hybrid of all possible Lewis structures. Resonance stabilizes the molecule. Rules for drawing resonance structures. Draw first the Lewis structure that maximizes octets. Move electron pairs from outside atoms to share with center atoms. If central atoms, second row, only move in electrons, you can move out electron pairs from multiple bonds. Formal charge equals valence electrons for the atom minus number of lone pair electrons minus 1/2 the number of bonding electrons. An example is NO2 plus 1, illustrating the calculations for formal charge per atom. Here, an alternative structure of NO2 plus 1 and the calculations for formal charge per atom. Comments on formal charge. Sum of formal charge is the overall charge. Formal charge should be as small as possible. The more zeros, the better. Negative formal charge, usually on most electronegative element. Formal charge of same sign on adjacent atoms is unlikely. Hint 1. Major species have all atoms with 0. Negative formal charge on the most electronegative element, or positive formal charge on the least electronegative element. Hint 2. Species with formal charges on elements greater than 1 or less than -1 are always minor species. Here is an electronegative table for your aid. Here is the solution. Structure A, B, and C are shown, but B is the major structure because it is not only the one that has the most neutral atoms, but also has the positive charge on the least electronegative atom, N. Here is a practice exercise. Draw all Lewis resonance structures for CNO-. Assign all formal charges and circle the major species.